Yeah, so thanks for having me here. It's great to be here. And so I'll be talking about some joint work together with Rolando LaPlaca and Aram Harrow at MIT, as well as with Alex Dalzell and Fernando Brandao at Caltech about phase transitions in the complexity of classically simulating random quantum circuits in 2D. So first I should give some motivation for why we should even care about classically simulating random quantum circuits. And I think a good place to start is this quote by Feynman from 1981, in which he points out essentially that nature is quantum, not classical. So if we want to simulate nature, it makes sense to do so with a quantum simulator. And this makes sense to us because we know that in general, the state of a quantum system requires an exponential number of parameters to specify. So a naive classical simulation algorithm will come with an exponential overhead, which will quickly become intractable. But we also know that this is not the full story, because there are plenty of examples of interesting quantum systems that actually do admit efficient classical simulations. And it makes sense to really understand these sort of counterexamples to Feynman's sentiment here in order to understand when we can expect quantum speedups. So just to list a few of these, obviously we have models in physics and chemistry which are exactly or approximately solvable. The Gottesman-Knoll theorem tells us that Clifford circuits can be simulated. Something that will be relevant later in this talk is that for one-dimensional quantum systems, if they're sufficiently unentangled in some sense, they can be efficiently simulated via matrix product states. Also, some classes of quantum circuits that have sufficiently high noise rates can be classically simulated. So that's just a partial list, but one thing that we do in this work is we essentially add another item to this list, namely random 2D quantum circuits of sufficiently low depth. And I'll talk later about what I actually mean by that. So that's sort of a more philosophical motivation, but for a more immediate motivation and maybe more practical motivation, we can look at this idea of quantum computational supremacy, which essentially refers to a quantum device performing some well-defined computational task, which is beyond the capabilities of classical computers. And one of the leading proposals for demonstrating this involves random quantum circuits. And in particular, probably a lot of you have heard of Google's 2019 claim to have demonstrated quantum computational supremacy. And their experiment, which they based this claim on, involves random 2D quantum circuits. And no one is really challenging their claim that they seem to be doing something that we can't match with classical computers today. But there's also a deeper question here of whether maybe there's some classical algorithm lurking out there which no one has discovered yet, which can simulate their experiment. And this is also related to the question of whether their experiment really challenges the extended Church-Turing thesis, which essentially posits that classical computers can simulate any other realistic model of computation with only polynomial overhead. And I think that the evidence that their experiment and similar experiments are challenging the extended Church-Turing thesis is fairly weak right now, just because we don't have a great understanding of how hard this random circuit problem is for classical computers. So it makes sense to study this problem in a more formal and asymptotic way. So now I'll actually define the specific computational problem I'm talking about. So this is known as random circuit sampling. And so the idea is we'll start with a 2D array of n qubits. I'm saying qubits because in general, the local dimension could be greater than 2. And I'm also illustrating this with the cartoon in the bottom half of the screen. So we imagine we start with some L1 by L2 array. And next we apply some random circuit to these qubits consisting of some number of layers of 2 local Haar random gates. And if you don't know what Haar random means, you should just think of it as uniformly random. So after we apply these random gates, then we perform computational basis measurements on all sites. So to illustrate this, we can imagine these red lines represent the first layer of gates. So all of these are independent, identically distributed random gates. And then these green lines can represent a second layer of gates. And then this represents a third layer of gates. And actually, this pattern of gates that I just demonstrated here is known in the literature as a brickwork architecture. And I'm mentioning that because I'll return to this specific architecture throughout this talk for illustrations. And this is a depth 3 architecture because I applied 3 layers. And okay, so after we apply the random gates, we perform measurements on each site, which I'm representing by the red X's. And of course, when we perform these measurements, we get some random output string distributed according to some distribution. And the random circuit sampling problem is just to generate a sample or multiple samples from the appropriate output distribution. And it should do this at least approximately, and it should work with high probability over the realization of random circuit. So just to recap, we generate a random circuit C that corresponds to some output distribution, which I'm calling D sub C. And right. Oh, I just saw a question. Oh, why is the third layer sparser? So yeah, I guess there's a few reasons for that. So I guess primarily, this particular brickwork architecture is known to be universal for measurement-based quantum computation. So basically, this is getting a little bit technical, but essentially the reason why we're looking at this particular architecture is for 2 reasons. So one reason is that it is non-trivial in some well-defined sense, and namely that this architecture is universal for quantum computation with adaptive measurements. And in practice, why we look at this architecture is that our simulation algorithm, which I will get to shortly, performs well on it. Basically, the fact that it's sparse allows our algorithm to work very well, and it allows us to do numerical experiments. But yeah, there's really nothing particularly special about this architecture. It's really just something that I'm using as an example, but yeah, it is arbitrary, I would say. Okay, I'm having a technical difficulty closing the Q&A box on my screen. Oh, okay. All right, so the computational task then is to generate samples from the output distribution with high probability over random circuit and with maybe small approximation error, where I'm not defining these precisely, but they can be made precise. Okay, so in a moment, I'm going to claim that the random circuit sampling problem for this depth 3 brickwork architecture, for example, is easy classically. So I should first try to convince you that that should be interesting in any way by giving you some reasons for why that might be hard. So we can first take a step back and ask about how hard is it to classically simulate arbitrary 2D quantum circuits. So instead of the gates being chosen randomly, maybe the gates can be chosen in some worst case way or adversarially. So this question was studied by Turhal and DiVincenzo back in 2002. So a consequence of their result is that depth 2 circuits are always classically simulable. But on the other hand, once you hit depth 3, there cannot exist any efficient polynomial time classical algorithm for this problem unless the polynomial hierarchy collapses. And if you don't know what the polynomial hierarchy is, all you need to know is that that's a consequence that's considered highly unlikely. So their work indicates that we should definitely not expect to find an efficient classical algorithm that works even for worst case configurations of gates. But then there's also some plausible reasons to believe that random gates should be essentially the worst case. And so to go through some of these from the algorithmic perspective, basically all of the examples we know of efficient classical algorithms for simulating non-trivial quantum systems do so by exploiting some special structure present in the quantum system. And intuitively, we might expect that if the gates are random, this should wash away any structure that allows simulation to happen. And from the physics perspective, we know that entanglement spreads quickly in random circuits, and more entanglement is associated with more difficulty of simulation. And from complexity theory, besides the Turhal-DiVincenzo result that I mentioned, there's a much more recent result due to Bouland et al. From 2018, which essentially proves that for the alternative computational task of computing specific output probabilities rather than sampling, for this problem, they prove that random gates essentially are the worst case. And in particular, they prove that for this alternative problem of computing output probabilities, this should be sharp P hard even for depth 3 circuits. And if you don't know what sharp P hard means, you should just think of it as really hard. So all of this taken together paints a pretty plausible picture that random circuits should be very hard to simulate classically. They should be perhaps virtually as hard as worst case instances. And I think a lot of this intuition is helped form the basis of why random circuit sampling was put forward as a good quantum computational supremacy proposal to begin with. But one consequence of our work here is that this sort of intuition should not be trusted necessarily on its own. So now I'll describe our results. So we propose two classical algorithms for this random circuit sampling problem, which are applicable for constant depth circuits. So for this talk, all the 2D circuits that you see, you should think of them as having constant depth. So we have two classes of results. We have provable results and also conjectures supported by evidence. So on the provable side, we can show that at least for special cases of 2D depth 3 random circuit architectures, our algorithms indeed are efficient and they work as they should. And this applies even to depth 3 architectures, which are non-trivial in the sense that the hardness results of Turhal-DiVincenzo and Bouland et al. That I described before, those hardness results still apply, but nonetheless, they can be simulated provably by these algorithms. But we also conjecture that the algorithms are efficient much more generally, despite not being able to prove this rigorously. So we conjecture that that the random circuit sampling task is classically tractable using these algorithms for sufficiently shallow circuits more generally. And we also conjecture that there's an interesting catch here, which is that these algorithms experience computational phase transitions from efficient polynomial time regimes to inefficient exponential time regimes as parameters like the circuit depth and the local qubit dimension are increased. That is, once they surpass some critical values, we expect this computational phase transition into an inefficient regime for these algorithms. And these critical values you can think of as constants that in general could depend on the details of the circuit architecture. Okay, So with that being said, now I will describe how one of these algorithms works. So the high-level idea or the high-level strategy here is we're going to reduce the problem of simulating a 2D circuit into a problem of simulating a 1D circuit. And then I'm going to claim that this 1D circuit can be efficiently simulated classically for at least if the original 2D circuit has sufficiently low depth. Okay, so I'm going to illustrate this with the brickwork architecture that we saw before. So recall that we have some first layer of horizontal gates, and then a second layer, and then a third layer of vertical gates. And then remember that at this point, we measure all of the sites. So a first observation is that it doesn't matter what order we perform the measurements in. We could measure column 1 first, and then column 2, column 3, etc. So we could do column-wise measurements until we measure everything. So the strategy of the classical algorithm is going to be to simulate these column-wise measurements. So first, we want to start by simulating the measurements of column 1. So to do this, we first need to simulate the application of gates which lie in the causal cone of column 1. Or in other words, we have to simulate the application of all gates that could possibly influence the reduced density matrix on column 1. So in this example, you can show that that corresponds to these gates. So we have to simulate the application of these gates and then simulate measurements on column 1. And so then we move to column 2, and we want to do the same thing. We need to apply all of the gates that can possibly influence column 2, which have not previously been applied. So you can show that that would be these gates in this example, and then simulate measurements on column 2. And note that every time we simulate, in every round of this, each round consists of some measurements on a column, which then induce some new quantum state on the remaining columns. So what I've done here, after we measure column 2, we have now induced a state on columns 3 and 4. So there's a question, what does it mean by random quantum circuit? Right, so basically the setting here is that you can imagine that beforehand we specify a pattern of gates in the quantum circuit. So that's what I'm calling the architecture. So we specify a particular architecture, and then what I mean by a random circuit, given that architecture, is that each gate is chosen according to the Haar distribution. Or you can just think of the Haar distribution as basically a uniform distribution over all possible 2 local unitaries. Yeah, so that's all I mean by random circuit. Fix an architecture, and then given the fixed pattern of gates, each gate is chosen uniformly at random. All right. Okay, so then the algorithm keeps progressing in this way at each stage, applying gates in the backwards causal cone, or in each stage, applying gates that can possibly influence the reduced density matrix on the column under consideration, and then simulating those measurements, and just iterating this until all columns have been simulated. So another way of thinking about this is, once we've done this reduction, we've essentially reduced the problem to simulating some sort of effective 1D dynamics. So if there are L sub 2 columns originally, then we essentially have this sequence of L sub 2 states that we're progressing through, and we progress through these sequence of states according to these iterations that consist of applying some new random gates and then doing some measurements. So this idea is actually fairly simple. And if you're familiar with measurement-based quantum computing, it is quite similar to the idea there. So the tricky thing is trying to understand why this effective 1D dynamics should possibly be classically simulable. And so to this end, we can turn to this observation of Vidal, namely that if you have a 1D process like this, if the entanglement stays sufficiently low in some sense, then it's possible to classically simulate the evolution via what are called matrix product states. And if you don't know what matrix product states are, you could just think of it as a classical data structure that is good at efficiently describing one-dimensional quantum states that don't have much entanglement. So basically, the strategy of this algorithm is to look at this effective 1D dynamics and hope that the entanglement throughout this effective 1D dynamics is sufficiently low so that efficient simulation via matrix product states is possible. So on the next slide, I will try to motivate why that is plausible. That is why it's plausible that the entanglement stays low in such a process. But here I'll just note that, as I mentioned before, we can, for some special cases of architecture, we can rigorously prove that the entanglement stays low in this process. In fact, so low that we can be sure that the classical simulation works. All right, so now I'll try to motivate why we might hope that the entanglement in this effective 1D dynamics stays low. And so for this, we can start by recalling from the previous slide that in each step of this process, in each iteration, we apply, or rather the classical simulation algorithm simulates the application of some random gates, and it also measures some subset of the sites corresponding to whatever column is currently under consideration. There's a question. Is the sampling task conditioned on a chosen random circuit or sampling from the joint distribution of? Right, so the sampling task is conditioned on the chosen random circuit. Yeah, you can think of it as we fix a realization of the random circuit, and then for that fixed realization, we want to generate samples from the output distribution corresponding to that fixed realization. Yes. And yeah, the hope is that we are able to do that with high probability over the realization of the random circuit. Right, so I mentioned that we have these alternating rounds of random gates and measurements. So now we can observe that this is actually heuristically, at least, quite similar to a family of quantum dynamics which have been studied in a very large number of recent works in the past couple of years, mainly from the condensed matter physics community. And we can call these processes random Unitarian measurement processes. So I'll tell you what that is about. So the idea here is we start with some, see a question. What happens if there are no measurements? Well, I guess if there are no measurements, then the computational problem isn't even well defined. Like we're specifically interested in this random circuit sampling problem, which is to perform the unitaries and then measure everything at the end. And yeah, so without the measurements at the end, we're basically looking at a totally different problem. In fact, like we don't even have a notion of what the computational task is in this case without further specification. Right. Okay, so then, yeah, so these random Unitarian measurement processes that have been studied mostly from the condensed matter community recently, looking at this cartoon, you can imagine that we start with a 1D quantum state on the left-hand side, and then we evolve over time according to alternating rounds of two local random unitaries, as well as measurements, which are represented by the red dots. And in general, these don't necessarily need to be computational basis measurements. They could be more general, weak measurements. So we have these two sorts of layers, random unitary layers, as well as measurement layers. So an interesting question here is, how does the entanglement behave in such a process? Because we essentially have two competing forces. The unitaries tend to increase the amount of entanglement present in the system, but the measurements tend to destroy entanglement. But in general, if they're weak measurements, they won't necessarily destroy all of the entanglement. So the question is, which of these effects wins out? On the one hand, we could imagine that the entanglement just grows to some very large value. Or on the other hand, we could imagine that the entanglement quickly saturates at some smaller value and stays at that smaller value in equilibrium. And the answer from this line of work is that there appears to be a phase transition between these two regimes. So there appears to be a phase transition from an area law regime for the entanglement and a volume law regime for the entanglement, as measurement strength is tuned, or also as the local dimension is tuned. And if you are not familiar with the terms area law and volume law, you should just think of area law as meaning very low entanglement and volume law as meaning very high entanglement. And this is very interesting from our perspective, because this sort of circuit that I drew in this cartoon looks a lot like, at least on a heuristic level, it looks a lot like the effective 1D dynamics that we saw in the previous slide, with these alternating rounds of applications of unitaries and measurements. And another interesting connection is that in the effective 1D dynamics, if the depth of the original 2D circuit to be simulated, if that depth is increased, that has the effect of lowering the effective measurement strength in the associated 1D dynamics. So when all of this is taken together, it suggests that perhaps if the depth is sufficiently low, then the effective 1D dynamics is in an area law low entanglement phase, and simulation should be possible. But then as the depth surpasses some critical value, then there should be perhaps a phase transition in the associated effective dynamics, and simulation should become inefficient. Okay, I saw there was a question. Okay, I guess I'll answer it later. It's not there anymore. All right, so moving on. All right, so I mentioned before that we can rigorously prove that the entanglement is in this area law low entanglement phase for some special cases of architecture. So I'll just mention the sort of architecture that we can rigorously show this for. And we call this an extended brickwork architecture, because it looks a lot like the brickwork architecture, but sort of elongated. So in particular, if you'll think back to the brickwork architecture that I told you about before, we have these two layers of horizontal gates, and then we have a layer of vertical gates. And the idea in the extended brickwork architecture is it's the same thing, except the spacing between the vertical gates is much larger. So in particular, the spacing is actually increasing as a function of the number of sites, n. So this architecture, we can rigorously prove that the algorithm works for this. And I'll also mention that the architecture, it's not like spacing the vertical gates out makes the architecture trivial in some sense. These hardness results like by Turhal DiVincenzo and Bouland et al., they still apply. So we know from those results that we should not expect an efficient classical algorithm that works in the worst case. And also we know that it should be hard to compute output probabilities, even in the average case for random gates. But nonetheless, via this algorithm that I described before, efficient approximate simulation for the sampling problem, at least with high probability over the random circuit realization, that task is easy classically. So I see a question. What do you mean by weak entanglement? Is there a kind of measurement which does not destroy the entanglement? Yeah, like I guess, I mean, for example, you could imagine, one way to think about it maybe is if you want to think about projective computational basis measurements, you could imagine that what I'm calling a weak measurement entails, say you couple the particle to be measured with some ancillary particle, according to, I don't know, some random unitary or something. And then maybe you do a computational basis measurement on the ancillary particle. So that would be sort of one way of thinking about what a weak measurement is in terms of projective computational basis measurements. So that kind of measurement in general would not destroy all the pre-existing entanglement like a projective computational basis measurement would. Yeah. All right, so I think there's some more. Let's see. Oh, okay, never mind. All right, so moving on. So I mentioned that this sort of architecture is classically simulable, provably, but unfortunately, this architecture is kind of unnatural. So it's non-uniform in the sense that the layout of the architecture itself is defined as a function of the system size. So what about more natural uniform architectures? So for example, what about the original Brickwork architecture that I told you about before? So unfortunately, we can't rigorously prove efficiency in that case, for example, or for any uniform architecture for that matter. But we do believe that the algorithm is efficient more generally. So we collect numerical and also some analytical evidence for that. So I'll tell you a bit about that. So saying a few words about numerics, this plot here is essentially showing how much entanglement is present in the effective 1D dynamics associated with the Brickwork architecture, the ordinary Brickwork architecture, as a function of system size or side length, which I call L along the x-axis. So basically, for different side lengths L, what does the entanglement saturate at after the circuit has been allowed to run for a long time? So more precisely, I'm actually plotting the average half-chain entanglement entropy in the effective dynamics after it's allowed to equilibrate. And I'm also plotting different Renyi entropies, but the only important takeaway here is that the dependence of the entanglement present in the system as a function of the system size appears to be virtually non-existent. So this is strongly suggestive of an area law phase for the entanglement entropy in the effective 1D dynamics associated with the Brickwork architecture. So this is strongly indicating that our simulation approach might work and it might be efficient. And indeed, we implemented the algorithm that I described to you on a laptop, and we were able to pretty easily simulate Brickwork architecture instances of size up to 400 by 400 with only small simulation error. And this particular task of simulating a 400 by 400 Brickwork architecture is highly intractable for previously known simulation algorithms that we are aware of based on tensor network contraction, for example. And another nice feature is that the algorithm that I described, without getting into details, it is self-certifying in the sense that it's able to keep track of how much error it's making. So it's able to bound its own simulation error. So that lets us have confidence that it's actually working properly. I think I'll skip over the point that I was going to make here in the interest of time. So just to say a few words about another analytical tool that we use to study this algorithm is, so this is via some mapping from random quantum circuits to classical statistical mechanical models. So I only have time to give a very high-level flavor of what this is about, but the idea is that every random quantum circuit can be associated with a classical statistical mechanical model where the StatMech model has two classical spins in place of each random unitary in the original quantum circuit. And the nice thing about this mapping is that certain entanglement properties of the output state of the circuit can be associated with certain physical properties of the StatMech model. So we apply this mapping to the setting of constant depth 2D random circuits that we're interested in. It was first applied by Hayden et al. In the context of random tensor networks, and then later by Nahum et al. In the context of random quantum circuits. And then we're applying it for shallow depth 2D quantum circuits. And the interesting thing that we find in this mapping is that there appears to be a direct correspondence, or maybe I should actually say indirect correspondence, because this is kind of heuristic, between the phase of the StatMech model and also the amount of entanglement present in the effective 1D dynamics of the associated quantum circuit. So this gives us another tool for understanding this algorithm. The Brickwork architecture, for example, the ordinary Brickwork architecture, that is, we find that the associated StatMech mapping is in a disordered phase, which is suggestive of an area law for the entanglement entropy in the effective 1D dynamics. And also we find evidence that there is a phase transition in the classical StatMech model as the qubit dimension or the circuit depth is increased or tuned, I mean. So this is sort of corroborating evidence for our prior reasons of expecting that there should be some computational phase transition as a function of depth and local dimension. And then I was going to say something about the other algorithm that we proposed, but I'll just skip over that. And yeah, maybe in the interest of time, since we're already over by a couple of minutes, I'll just list some open questions here and there. Thanks.